Question is from GATE 2022, question number 38. I have not mentioned the session. I guess session 2 was there. So basically what the question says is a planar 4-bar linkage mechanism with 3 revolute kinematic pairs and 1 prismatic kinematic pair is shown in the figure, where AB is perpendicular to C and FT is perpendicular to C. The T-shaped link CDEF is constructed such that the slider B can cross the point D, right? Now and CE is sufficiently long. Now for the given lengths as we shown, the mechanism is, they have given some options like a Grashof chain with links AG, AB and CDEF completely rotatable about the ground link FG. Then the second option is a non-Grashof chain with all oscillating links. Then a Grashof chain AB completely rotatable and oscillatory links AG and CDEF. And last is on the border of Grashof and non-Grashof. See what we have discussed is all the turning pairs were there, where we have classified Grashof links and different mechanism based on that Grashof's law of S plus L, right, less than or equal to P plus Q. So whatever we have discussed in this Grashof's law, at that particular point of instance all the 4 pair were turning pair, while here you are having 3 revolute kinematic pairs and 1 prismatic kinematic pair, right? So one is sliding, right, and the other 3 are this 1, 2 and 3 are you are having this as revolute pair, while one is this particular one is sliding pair. So here if you apply this one, then you are having shortest link as 1.5 and this is this is 5 centimeter, right? So if you add this two, it is 6.5, which is not less than or equal to the sum of remaining 2, that is 3 plus 3. So you can directly say that a known Grashof chain with oscillating link, but that is not the correct answer. Why? Because here you are having one sliding link, right? So in that case what will happen is this 1.5 centimeter is the shortest link and the link beside the shortest link is fixed. So here you will have this first option is the correct option. All this AG, AB and CDEF can completely rotate around the fixed link FG. So this is how you are having this particular question, right, from the Grashof law, which we have discussed in the last session. Next one, before that let me check if anyone is there.
Hello sir.
Yes.
So this session offline videos is available?
That we will see and discuss at the end, right? Whatever doubts you are having, right, we can discuss it at the end, right? Or you can type in the chat box. I will look into it. While I will ask you to solve the question, I will look into the chat box. Is that okay? Hello
Sir.
Yes
Sir, I have not attended the previous class, sir.
so the means I will see whether it will be possible to make you available those lectures, but this lecture is what we can say different content, right? And whatever we are going to solve the questions today, for that the session we are starting now is enough to solve the questions we are going to see today. Is that okay?
Okay, sir.
Okay.
So please upload in the website, sir, lecture video, sir.
Sorry?
Sir, lecture video, sir. Please upload in the website, sir.
That is what I am telling. Whenever that particular platform will be there, over there we will share this. But for that first, I guess some discussion forum or that kind of official platform needs to be generated. So the authorities are doing those things. So whenever it will be done, this will be shared with you. Okay?
Yes, sir.
Okay. So let us continue. So here the next is the steering gear mechanism is also important thing, right? So here if we see the condition for perfect steering, so whenever a vehicle is taking a turn, the steering mechanism is applied or provided on the front wheels, right? So here on the front wheels we are having this steering mechanism provided. So whenever this particular wheel is going to take a turn, both wheel is going to make certain angle, as it is mentioned, inner wheel and outer wheel, right? Theta and phi. So when we are taking a left turn, this can be considered as inner wheel, this can be considered as outer wheel. So inner wheel is making an angle of theta and outer wheel is making an angle of phi. So why we are deriving this condition for perfect steering is whenever vehicle is taking a turn, there must be what we can say, that particular thing must be done without skidding, right? Without skidding, right? So wheels should not skid, otherwise there will be more
What is the meaning of skidding, sir?
Sorry?
So what is the meaning of skidding?
Skidding means it will have friction with the ground and it will not perfectly what we can say take.
Sir, is there any difference between slipping and skidding?
Slipping is, I guess, we can say almost means same, I guess. Slipping or skidding,
So you can say
almost.
slipping.
Yes. So it should
Okay,
not
thank you, sir.
have that friction. Yes, it should not have that friction while taking a turn, right? So for that
So there is no friction, sir.
sorry,
So there is no friction.
there is
सर जो सर स्कीडिंग सर.
yes. Hello.
Yes sir.
Yes.
Yes sir.
So let us first see this, right? So here in this particular figure, as you can see, you are having two different triangles, right? Triangle PBI and triangle PAI, right? So here your cot phi will be this PA over AI, sorry, PA over this PI, right? And cot theta will be PB over PI. So when you go for this cot phi minus cot theta, then it will be this PA minus PB upon PI, right? So PA minus PB is nothing but this distance C, which is given here. This is base, or what we can say, the distance between this axle, and PI is nothing but B, right? So this is how, in order to avoid this skidding while taking a turn, condition for perfect steering is given with cot phi minus cot theta is equal to C by B, right? And B is the distance between front and rear wheel, right? So this is how you are having this condition for perfect steering. Now if you go for there are different types of mechanism, steering gear mechanism. So if you see this Ackermann steering gear mechanism, so in that Ackermann steering gear mechanism, this is the mechanism, right? A, B, C, D. So all the pairs are turning pairs in this Ackermann steering gear mechanism, and it is shown that when it is taking a left turn, how this mechanism will look like. The changed position is shown with this dotted lines, right? Yes.
Sir, I have one doubt regarding turning pair mechanism.
Can we discuss it at the end?
Okay, sir.
Okay. Now the second one is this Davis steering gear mechanism. So as you can see, in Davis steering gear mechanism, you are having two sliding pairs here, right? sorry, this is a slider, this is a slider. So this is how in your this Davis steering gear mechanism you are having two sliding pair and two turning pair, right? So Davis steering gear mechanism is having more perfect condition for steering, or it is more exact rather, right? But as it is having the sliding pairs, it is not generally used because sliding pairs are having more wear and tear. So this Davis steering gear mechanism is not generally used, right? So this is how you are having this different kinds of steering gear mechanisms, right? So once you are done with this, then we can start with our main today's topic, that is displacement, velocity and acceleration analysis. So in that there are various methods. First method we are going to see is this instantaneous center method, right, for drawing your velocity diagrams and all. So instantaneous center method means whenever any particular body has relative motion with respect to other body, then it can have a simultaneous motion, right, like rotary as well as linear motion, right? So when you are considering the motion of a particular link as a rotating motion around a particular center, then it is considered as this particular instantaneous center. So in this given figure, this figure if you see here, you are having a body P which is having this rotational motion with respect to this particular body Q, right? So here in that rigid body P, you are having 2 points A and B, right? So if you take these 2 points, these points are having a rotating motion around a fixed point I, that is known as instantaneous center. How you are going to get that point is, if you take a linear velocity of A at a particular instant, right, at a particular instant, right, you can take velocity of A or linear velocity of A in this direction as it is mentioned here. Similarly, at that instant, velocity of B or linear velocity of B must be in this particular direction, right? So once you take a perpendicular from both this particular points A and B, you will find this intersection point I, right? And that is the point around which this both the points are actually rotating. That is why it is known as instantaneous center of rotation for this particular points. So this is how you are having this instantaneous center of rotation, right? So once you have idea about what is this instantaneous center of rotation, then you can see this Kennedy's theorem, right? So Kennedy's theorem is regarding when you are having two different links, right, and you are going to add third link, then the third particular link have their instantaneous center must lie on the what we can say that straight line joining the instantaneous center of rotation for the other two, right? So that we will discuss by this example. Here you are having three different links, P, Q and R. P, Q and R are three different linkages. Link R is fixed link. P and Q are having motion or relative motion with each other. So here actually this P is having a rotation around this fixed point PR, and Q is having a fixed rotation around this point QR. So now if you take a particular point where they are meeting, like this PQ, so this PR and QR are nothing but instantaneous center of rotation between link P and R and between link Q and R, right? This PR and QR are instantaneous center of rotation for this link P and R and link Q and R. Now if you go for this instantaneous center of rotation for link PQ, and if you assume it at this particular point, right, so here if you take consider this point PQ on link P, then the direction of what we can say linear velocity will be in this direction as it is mentioned as VP, and if you consider that point PQ on link Q, then the direction will be this one, right? VQ. So the same point cannot have two different direction of velocity, and hence this particular PQ cannot lie at any other point other than line joining this PR and QR, right? So this PQ must lie on this line which is joining these points PR and QR. So that is why this Kennedy's theorem says that whenever you are having this two links having their fixed point with any other link, and then the third instantaneous center must lie on the same line or on the straight line. That is what the Kennedy's theorem says, right? Now apart from that, you must have idea about number of instantaneous center, right? So whenever you are having any mechanism, then you must have a certain number of links, right? And from that you can calculate the number of instantaneous center. So if you are having number of link as 4, then number of instantaneous center will be 4 into 3 by 2 will be 6, right? So 1 second, if someone is there, right? So yes, so here
Sir, the formula of number of instantaneous center is NC2, na?
yes, or you can
Okay,
say
sir.
or you can say this n minus 1 by 2, same, right? So here 4 into 3 by 2, that is 6 only. So if you take this mechanism which is shown in the figure, that is 1 2 3 and 4, right? 4 number of links are there, so you will have total 6 number of instantaneous center, right? So here in case of this mechanism, whenever you are having turning pair, those two turning means those two links which are joined by turning pair must have their instantaneous center on the center line of the pin which is used to join those two. So here 1 2 2 3 3 4 and 1 4 are having their instantaneous center of rotation at the points, right, at which they are joined. So here here you are having this this 4 instantaneous centers straight away with you 1 2 2 3 3 4 and 1 4. Now in order to get this instantaneous center 1 3, what you have to do is you have to assume that you are having a link 1 and link 3, right, and you are adding link 2. So link 1 is having this 1 2 instantaneous center with link 2, and link 3 is having instantaneous center with link 2 3. So the instantaneous center 1 3 must lie on the straight line joining this 1 2 and 2 3, right? So this is why you have had this extended straight line. Similarly, you can see that link 3 and link 1 is joined with link 4 also. So it is having already link this instantaneous center of rotation link this 1 4 and 3 4. So here also you have to have the link force this instantaneous center of rotation in the line or straight line which is extended on this direction. So when this two line is going to intersect, you will have this particular instantaneous center of rotation 1 3, right? Similarly for 2 4, you have to have this extended lines on 1 2 1 4 and 2 3 3 4, right? For this you can also have one more trick, right? If you are having this 1 2 3 4, right, like this, if you can write like this 1 2 3 4, right? So here you are having this 1 2 2 3 3 4 and 1 4. Now in order to join this 1 3, what you have to do is you have to extend 1 4 and 3 4. Are you extending 1 4 and 3 4? Yes. And you have to extend 1 2 and 2 3. Are you extending 1 2 and 2 3? Yes, right? So like that, see, for 1 3, as I told you, you have to extend 1 4 and 3 4. Similarly for yes,
Sir, what is the instantaneous velocity?
sorry,
So what is the instantaneous velocity?
instantaneous velocity, actually, I guess whatever this instantaneous center of rotations are giving you, the data is for a particular configuration, and for a particular instant you are getting that. So whatever you are getting is that point of instant, the different linkages are having this different velocities which you are calculating. So that must be the thing, I guess, right? And through this analysis, actually, after calculating this velocity and acceleration, you are going to further calculate the forces acting on this links and all. So that is why it will be helpful to you in designing the dimensions and all, because after that force and all, you can have the stress acting on it, right? So this is how the material which you are going to use for making this links and all will come into picture, and ultimately we will be able to decide the cross section and the material. As per your material, you will decide the cross section and the material required to build that link to bear that stress which will be available from this velocity acceleration data, right? So right now we are discussing how you are getting this instantaneous center, how you are going to locate this. So for locate,
So,
yes,
so can you explain once again with that quadrilateral? I mean, the square with the circle.
square with the circle, na?
Yeah.
So yes, once again I'm repeating. Let me do it again. 1 second. So here, as I have told you, you are having this 4 links, 1 2 3 4, right? And you are locating the instantaneous center of location, right? So if you consider this is 1 2 2 3 3 4 and 4 1, right? And now you want to locate this 1 3. So in order to locate this 1 3, what you have to do is you have to extend this 1 4 and 3 4. Here this 1 4 and 3 4 you are extending. Similarly, you have to extend this 1 2 and 2 3. This 1 2 and 2 3 also you are extending in order to get to 1 3, right? Similarly, for getting this 2 4, what you are going to do is you are going to extend 1 2 and 1 4. So here for getting 2 4, you are extending this say 1 2 and 1 4 to getting in order to get this 2 4, you are extending 1 2 and 1 4. Similarly, you have to extend 2 3 and 3 4. So here 2 3 and 3 4 is extended in order to get this 2 4. So this is how you are having your location, or you need to locate the instantaneous center of rotation, right? So this is how you can locate it.
Of writing 1 2 3 4.
Sorry,
Is there any sequence of writing the points that you have written on the circle?
you can write in the same sequence as I have mentioned, huh?
Sir, if we choose 1 3 2 4, we will it not? उससे कोई problem नहीं होगा ना?
I have not tried actually, but you need to check. You need to check whether it is same or it is having any difference, right?
Okay, sir.
Okay. So now then moving to the next thing, that is rules for locating instantaneous center. As I have told you, whenever you are having any turning pair, your instantaneous center of location, instantaneous center of rotation will be located at this particular center line of the pin which is joining this link 1 and 2. If you are having a slider sliding on a particular surface, then as you can see, the instantaneous center of rotation will be at infinity, right? Because it is having parallel velocities to each other. So when you go for finding the intersection, you will have lying it at infinity. So for slider it is at infinity, and when any particular link is rolling, pure rolling on the other link, then you will find it at the intersection point, right? So this is how you are having the various location of instantaneous center of rotation. Here I have taken one problem from SS Ratan, right? So here So what the problem says is, in a slider crank mechanism, the lengths of the crank and the connecting rod are 200 mm and 800 mm respectively. Locate all the eye centers of the mechanism for the position of the crank when it has turned 30 degree from the inner dead center. Also find the velocity of the slider and the angular velocity of the connecting rod if the if the crank rotates at 40 radian per second. Right. So now here the first thing is to locate the all the eye centers, right? So that you know, right, how to locate the eye centers, right? So in case of this particular problem where inner dead center is at 30 degree, right, you can have this slider crank mechanism. Right here you are having a slider, right here you are having pin joint, here also you are having pin joint. If you say this as 1 2 3 and slider as 4, right, so your I12 will be here only. Here you will have your I12, here you will have your I34, which are connected by turning joint, right, and this here you will have I23, correct, and then you can have your I14 at infinity, because between 1 and 4 you are having this kind of relation, right, as mentioned in this figure B. So 1,4 will lie at infinity, so you can have your 1,4 at infinity, right, here and here, as it is already mentioned here. Now in order to get 1 3 and 2 4, as you have done in that 4 bar mechanism, here in slider crank mechanism also you have to extend, right. So for getting 1 3, what you are going to extend is 1 2 and 2 3. So here you will extend this 1 2 and 2 3. Similarly you will extend on the other hand 1 4 and 3 4. So here also you will have some extension. So this intersection will give you this I13, and similarly in order to get the 2 4, what you are going to extend is 1 2 and 1 4, right. So here 1 2 and 1 4 is there, so you will extend it, and you will extend this 2 3 and 3 4, right. So 2 3 and 3 4 you are having on this line, so it will be extended. So here you will have I24, right. So what you are asked is, you are asked to find the velocity of slider, right. So that is V4. So velocity of slider can be available from your this particular omega of link 2 and the distance I1 to I24, whatever distance between I1 to 24 will be there, you can calculate this linear velocity, right. Similarly for finding this omega 3, right, what you can do is, you can have this velocity at point B is known, right, at velocity at point 2 or velocity at point B, you can say, divide by this distance I13 I23. So this is how you can find the different things which is asked. It will be very time taking, because you have to construct it with particular scale and dimension as mentioned. So we are not going to do that now because it will take a lot of time, but you have to have idea that how this kind of diagrams are being constructed.
So can you explain this again, sir?
Sorry,
How the expression V4 equal to omega 2, that is written, please may you explain it? Expression of V4.
expression of, hello,
V4 sir, velocity of fourth link, V4.
actually velocity of fourth link is means connected to the what we can say this instantaneous center at 2 4, right, because this link 4 is there, right. Slider is link 4, correct. So
Yes sir.
so links force linear velocity is related to the what we can say, this link seconds that velocity, what we can say, this link seconds linear velocity. So link 2's this omega 2 is
Angular
given.
velocity.
Crank.
Angular velocity.
Yes, crank, for crank it is given, right? What is the angular velocity? I guess here it is mentioned a crank rotates at 40 radian per second, right? So from that, you once you plot this figure from this crank's angular velocity, you can get the linear velocity of slider, right? Because they both are assumed to rotating around the same instantaneous center, that is this 2 4. That is why you can go for this expression in order to get the linear velocity of slider, right? So this is how
Sir.
you are having this equation. Yes.
Sir, the values of I12 and I24 are the lengths of this construction.
I1224 means this distance, right? This distance here. I12, I24 is this distance, whatever is there.
Sir, can
One
we-
thing,
Sorry.
sir, I am asking that, sir, why don't we take the I14, like which you were telling that would be infinitive, but it's totally linkage, na, sir, 1 and 4.
Sorry, 1 and 4.
It's totally linked, na.
1 and
Isn't it linked? Yeah.
1 and 4 are linked, but it is linked this way as mentioned in this figure B. One is fixed and other is sliding. So whenever you are having this kind of combination, the instantaneous center of rotation will go at infinity.
Whenever it's linked between one would be fixed and one would be sliding, then that would be infinitive, right, sir?
Yes.
Okay, sir.
Okay.
Thank you.
Okay. So now with this, I guess we can go for the next one. Yes. Next is this relative velocity method. So in relative velocity method, actually what you will have is you can have whenever you are having a rigid body, right, it will have relative motion between each other on the same particular body. You can, as we have seen in that instantaneous center of rotation, in relative velocity method we will see how one rigid body is having the relative motion about that what we can say center of rotation or the fixed pivot about which it is rotating or like that. So for that we have directly taken this question. So here again you are having slider crank mechanism. So as you can see in this particular figure, you are having a configuration of an engine mechanism, right, and the dimensions are given for this crank, connecting rod, then a distance of center of mass from crank end, right, and then this AD is mentioned. This D is a point on the link. For that also they are asking to find velocity and all. That can be calculated by that simple rationalization of length of linkages and the data we are getting on that velocity diagram, right? So that is, we will see how we will get that, right? Then at the instant the crank has an angular velocity of 50 radian per second clockwise and an angular acceleration of 800 radian per second square. Now calculate the velocity of D and angular velocity of AB and acceleration of D and angular acceleration of AB and point on the connecting rod which has 0 acceleration at that instant, right? So whenever we are going to solve this kind of questions, we will have we have to draw this velocity diagram and acceleration diagram. So we will first draw the velocity diagram for this, right? And whenever you start drawing velocity diagram, what you have to do is whatever data is given, you have to check that how can we start calculating velocity, because velocity diagram will require that linear velocity. So if you find this velocity of A with respect to O, velocity of A with respect to O, it will be VA minus VO, right, vectorially. But as the point O is fixed, VAO you can directly mention as VA only, which is nothing but R omega, right? So do you know the link length OA? Yes, that is nothing but R, right? And omega is given, right, at which your this crank is rotating, that is given, right? That omega of this OA is also given. So once you have this data, you can draw this particular vector, right, which is perpendicular to O and G. I am putting both are fixed point, right? O and G here, O and G are fixed point, so that I am putting as fixed point. From that this VA we are going to draw, which is having magnitude of OA into omega OA, and direction is perpendicular to this link length OA. So this I have drawn in order to get the point A, right? So the very first vector you are going to draw like this. Once you have drawn this, then if you think of velocity of this point B with respect to A, then it will be perpendicular to this particular link length BA, right? So once you have your all the instruments with you, like this ruler scale or something like that, then you can transfer the direction, right, from this image to this image, and you can take this perpendicular to this AB and you can plot it like this. Right now we don't know the magnitude, right? So you can draw a line which is passing through point A and perpendicular to this particular link length AB. Once you are done with drawing this particular what we can say construction, which will give you your velocity of B with respect to A, right? But you don't know the magnitude, you have direction only. Now one more thing is there, the slider B is also having velocity with respect to this point G, which is horizontal, right, which is in horizontal direction. So if you draw a horizontal from point G, right, then you will have some intersection, and that is nothing but your point B, right? So here you are having this velocity of B with respect to A, and here you are having your velocity of B only, because again this G is fixed as O is fixed. So you can write VBG, or here you can write VAO or VA, right? It is same. Now one more thing,
The direction of
sorry,
how the direction of VBA is found out?
sorry, VBA
की डायरेक्शन मतलब उसका डायरेक्शन के बारे में कैसे पता लगा?
this direction of this VBA is actually I guess from we can say how this B is moving. Actually when this A goes in this direction, as it is mentioned here, relatively B will go upward, right? Actually, though it is actually at the same point, but relative to A it will be found that it is going up, right? If you try to visualize the mechanism,
Yes, sir.
right? So because A is coming in this direction now, so
हाँ, sir.
with
So how
rela-
it's will be found out?
sorry,
Inclination of VBA उसको कैसे पता करेंगे?
sorry, inclination of
VBA
inclination, as I have told you now, once you have this figure, in this figure you are having this link AB drawn, right, at a particular angle already, right?
sir.
You can construct this particular diagram. You are given the link length OA, given the link length AB, and this direction or this angle 120 degree. So with all this data, this AB is having a particular inclination that is already with you. Yes or no?
Sir, I want to ask there, sir, direction of VBA will be perpendicular to AB, link
Yes,
AB.
yes. It will be perpendicular to link AB. Yes, as here it is perpendicular to link OA, here it is perpendicular to link AB. Right?
Okay, sir, thank you.
So like that you are having this particular what we can say, this velocity diagram. Now here you have to locate point D also. So how you are going to locate point D? So for that, please mute yourself. In order to locate point B, you are having BD and BA with you. So here also you are having this BD and BA. So here BA is known to you from this velocity diagram. This small BA is known to you. Capital BD and capital BA are also known to you because this link lengths are already with you. You are given that what is AD, so you can calculate BD and AD. So and BD and BA are with you. These are physical link lengths, right? This is physical link length. Right. So as this is physical link length, you are having this BD, and now you want to calculate this BD because you want to locate point D on your velocity diagram. BA is already with you from the drawn geometry, and physical link lengths are having with you. So once you do this all calculation, you can have your point D on this line BA, and once you have that point D, you can also draw it from this fixed link in order to get the idea how this D is moving. So this is how you can have this velocity diagram, right? So once you are done with this velocity diagram, then you have to start drawing your acceleration diagram. In acceleration diagram, you will have two different acceleration. One is centripetal acceleration, right? Centripetal acceleration, and one is tangential this acceleration, right? So this acceleration may be centripetal or tangential. So this centripetal can be calculated from omega square r, while this is calculated on alpha into r. Omega square into r is same as v square upon r, right? Linear velocity upon r. And so linear velocities of all the links are with you from this velocity diagram now, right? So you can calculate the centripetal acceleration of almost all the components from this linear velocity. You know the link length, so you can calculate this. And angular acceleration is given for some of the components, so you can also calculate the tangential component for some of the links because angular acceleration is provided, right? So you can also calculate this. So if you talk about this link length OA only, then its centripetal acceleration will be towards, see, I will write like this OA, right? But here this direction of centripetal acceleration of A is from A to O, that is why this direction will be like this, right? And tangential will be perpendicular to this centripetal acceleration, right? AC and AT. Once you have both these components, right, then you can have the final acceleration of A with respect to O, right? Acceleration of A with respect to O, right? So let us say this as full acceleration of point A. Here little bit confusion is there, so I am writing acceleration.
Sir.
Yes, of A.
So the centripetal acceleration is in the direction of the link?
Is in the direction towards the center about which it is rotating, right? So both this velocity and acceleration diagram for this construction is there, right? So I am showing it to you now with this basic information and basic idea. You can see now this velocity and acceleration diagram for that particular configuration. This is velocity diagram and this is acceleration diagram, right? So velocity diagram is as we have seen. First OA is drawn, then this direction is drawn and this direction is drawn, and then this D point is located. So like this velocity diagram is drawn. Now in order to draw this acceleration diagram, how they have started is they have this point, fixed point, right, O1 and G1. Then the very first thing they have calculated or they have is this one, right? This O1 AO. Please mute yourself. Please mute yourself. Hello. Right, O1 to AO. This is nothing but centripetal. As you can see here, they have calculated it by V square by R. V you have already calculated from your velocity diagram, right? And
Sir.
link length is with u. So for that, as I have told you, first you are going to calculate this centripetal component, that is a linear velocity square divided by that link length, right? And then tangential will be calculated from the angular acceleration given. So angular acceleration is given for this crank, and it is perpendicular to this centripetal acceleration. So EO to E1 will be calculated then, so you can have this particular vector, right, O1 E1, which is nothing but acceleration of E with respect to O, right? So once you are having this, then you can have centripetal acceleration of B with respect to A. So that is again from B to A, right? So this is this direction which is mentioned here, and from there you can have again this particular perpendicular for tangential acceleration. Here this tangential acceleration's magnitude is not there, but you can have again acceleration of B with respect to this fixed link which is in horizontal direction. So this particular intersection will give you this point, and once you have that point, then from this you can have this final E1 B1 also, because here it is centripetal component, here it will be tangential component, right? And once you have this particular diagram, this O1 E1 B1, again you can locate point D1 as you have located in this particular diagram, right? So again you can locate D1 here, and you can have this particular joining of that D1 to O1, right? So this is how your this velocity and acceleration diagram is drawn, right? So yes.
Sir, could you please again explain about the acceleration diagram?
Yes, I can repeat it once again.
Even if you do it at the end of the session, that would be fine.
Okay. So then let us move forward, right? Because we need to solve questions also, right? So let us move forward for now, right? And I will get back to this slide at the end also, right? So now let us go to the next slide, that is acceleration analysis. So in acceleration analysis, actually we have seen how you are drawing this what we can say centripetal and tangential components. So now here actually when you are having two different motion of a link, right, like in your quick return mechanism, if you remember in crank and slotted lever mechanism, your slider is having linear motion as well as angular motion. So once your this kind of component is there in your mechanism, it must have Coriolis component, right? So we will see how that Coriolis component can be calculated. So for that, what you have to do is you have to assume that at a particular instant your this slider is on this link OAR as it is mentioned. So you are assuming that P on slider and Q on AR, right? So once you have this assumption, once you have this assumptions, once yes, so what you are assuming is now after an instant delta t, after an instant delta t, your link is rotated by delta theta, as you can see in this figure, r2 r dash, it has moved, right? So now if you calculate the acceleration along AR, then you must have idea about the velocities along AR, right, at a particular instant in which it is vertical, right, and at instant when it is moved by delta theta. So if you calculate it along AR, then as you can see along AR, this along AR means this direction, so vertical direction, you are having this if you see this different this diagram, because of angular velocity and because of linear velocity you are having changes, right? So you are having initial velocity, initial distance r from this point A of your slider P, right, and this angular velocity omega. These are initial what we can say parameters. After this delta t, what you are having is v dash, r dash and omega dash, right? So your v dash is nothing but your initial v plus f into dt. F is nothing but linear acceleration. Your r dash is nothing but r plus delta r, and your omega dash is nothing but omega plus alpha delta t, right? So this is how you are having various parameters, right, at a particular instant and after this delta t, right? So if you see, you are having this change in velocity due to this linear velocity and due to this particular angular velocity. So now here if you check along the this AR, acceleration after delta t is this v dash cos delta theta, means velocities are there actually. This is v dash cos delta theta minus omega dash r dash sine delta theta. This is after this delta t time. So previously it was what? Previously it was v only, as we have mentioned here. So this is change in velocity and you are calculating acceleration. So this change in velocity and in the denominator delta t will give you this acceleration along AR. Now what you are going to do is you are going to put all these values of v dash, r dash and omega dash in this equation, and as delta theta is very small, right, it is very small, right? So your cos delta theta is becoming 1 and sine delta theta is becoming delta theta in your this calculations, right? So when you put these assumptions, cos delta theta is 1 and sine delta theta is delta theta, then you will end up calculating your acceleration along AR as nothing but f minus omega square r, right? I am not writing the full because it will take too much of time, but when you will do this you will find this, right? So acceleration along AR will be like this, and acceleration perpendicular to AR will be, one second, acceleration.
Sir.
Yes.
So what is the F here?
F is, as I have mentioned here, F is linear acceleration. F is linear acceleration, right? So
Thank you, sir.
okay, so here if you go for this perpendicular to AR, means in this horizontal direction, so that you can see at after this delta t you are having v dash sine delta theta plus omega dash r dash cos delta theta, right? And before delta t it was omega r, right, in this direction perpendicular to AR. So now again you put values of v dash, r dash, omega dash and put cos delta theta is equal to 1 and sin delta theta is equal to delta theta, then you will end up with equation 2 omega v plus r alpha, right, where this omega v, 2 omega v is known as Coriolis component. Now Coriolis component is considered positive when your this rod or slotted lever is having this clockwise direction and slider is having outward direction. At that time it is positive. Or your this particular link or the slotted lever is having anti-clockwise direction and your slider is having inward direction. At that two instant it is considered as positive, while for the other two things it will considered negative. Means if your link is slotted lever is having anti-clockwise direction and lever is moving outward, means this component will be negative, this Coriolis component. And if your this link is having clockwise direction and your this slider is moving inside, then also it is having that negative component for your Coriolis component. Now once you have this idea, then you can go for drawing this velocity and acceleration diagram for crank and slotted lever mechanism also, right? So here what they have done, this velocity diagram, I guess you all can now be familiar with this one. How they have drawn this is O, A and G are already fixed points. As you can see, O, A and G are fixed points, so they have taken this as fixed. The very first thing what you can do is you can draw as it is in this clockwise direction. You can draw this VPO, right, because it is P with respect to O, right? Similarly, what you can do is you can have idea about the direction of this what we can say, this Q with respect to A, right? So Q with respect to A will be in the direction perpendicular to this link, right? So this link's perpendicular direction, you can draw a link over here, right? And this Q with respect to P, Q is on AR and P is on slider. So when you talk about the velocity of Q with respect to P, then it will be along the length or along the link AR only. So you can draw a line parallel to that AR from this point P in order to get this VQP, and this is nothing but VQA. Now R, how you have got, similarly as you have got that point D, RO upon QO is nothing but this, or A, right, that link length upon RQ. So all these things will be given, so that is going to help you in locating this point R. So once you are locating the point R, then the velocity of R with respect to S will be in the perpendicular direction to this link SR, right? So you can draw a perpendicular from this point R, and velocity of S with respect to G will be in horizontal direction. So here you can again put this horizontal, so it will intersect at this point. So this is how you are going to locate your point S, right? So this is how you can have your velocity diagram. So once you have your velocity diagram, then you can start with your acceleration diagram. In acceleration diagram also, the very first component you will have is this FPO, right? This is centripetal acceleration of point P with respect to point O. So as it is O1, P1 is towards O, right? Now once you have this, then what you can do is you can have this particular this location, sorry, this FCRPQ is the next thing you can draw. That is from the 2 omega v you can draw this, and it will be perpendicular to this link AR, right? So this perpendicular to this link AR, and as it is coming this direction, the direction will be towards this, right? Because we are considering it as positive. So as it is going in clockwise, this will go outward and it will be perpendicular to this AR in this direction. So once you have magnitude of this, you can draw this. After this, for the other component which is perpendicular to this what we can say Coriolis component, we can draw that, right? But we don't know the what we can say magnitude, so we simply can draw the line which is perpendicular to this, right, from this point, right? And it is going to cut this horizontal line from this P1, and you can locate this point Q1, right? So once you have this point Q1, then you can again locate this point R1, and for R1 again you can go for centripetal and tangential component. Centripetal will have direction from S to R, as it is mentioned here, from S to R, and then perpendicular to this you can have the tangential component, and S is again having acceleration with respect to G in horizontal direction, so you will draw a horizontal line and it is going to give you this point S1. So this way you can complete your acceleration diagram over here also, right? So once you are done with all this, then you can start with this questions. Yes,
Sir, sir, how we can physically understand the Coriolis effect of the acceleration?
Sorry.
How we can physically understand, as we know that in winds also the Coriolis effect. सर मैं उसको समझ नहीं पाता हूँ कि वो कैसे हो जाता है winds में Coriolis effect को physically कैसे perceive करें.
That actually I need to check, right? At the end, I guess you can tell me. I will note down this and I will check. Before that, we can solve this questions from gate, right?
Okay, sir.
Yeah.
जी, sir.
Yes. So let us see the questions. So here the circular disc has actually, it is not shown here, right? So let me show you. You are having a circular disc, right? So it is having a point O, and with respect to that you are having points A and B, right? So circular disc, and you are having this point O and point A and B, right? So here they are having that uniform angular velocity omega, right? Two other points A and B are located on the line OZ at a distance of RA and RB, right? RA and RB. This can be RB and this can be RA, right? So now the velocity of point B with respect to point A is a vector of magnitude omega r will be there, right? Its vector magnitude will be omega r, right? So omega rb minus omega ra, and the direction is same as the direction of motion of B, right? Point B. So that is correct for the 75th one. Here actually in the last option you are having omega square rb minus ra, right? So mistakenly here it is only omega, because acceleration of point B with respect to point A is a vector of magnitude again omega square rb minus ra, and the direction is from Z to O. As we know that it is the centripetal direction. Z may be somewhere here lying, right? And O is this point, as we have already discussed. This is point O. So this is how you are having your this first question, which is from I guess 2003, right? Now next is you are having this this figure. Yes.
The previous question is not solved.
Previous question.
Not solved.
Previous question solved. Now we have solved previous question.
Yeah, this one.
Yes. Yes. I have marked the correct answer. I have marked now.
Okay. Thank you, sir.
Okay. I have not generated a poll for that. Now I will generate for the next one. Let us see. Actually here figure is not given. Let me first draw the figure. The figure is like this. Here you are having this link, right? This link is given, which is having this omega 2, and this may be your link 1, this may be your link 2. Now we can read the question. In the figure shown, the relative velocity of link 1 with respect to link 2 is 12 meter per second. Link 2 rotates at a constant speed of 120 rpm. The magnitude of Coriolis component of acceleration of link 1 is. You have to calculate the magnitude of Coriolis component, right? And you have to type in numerical answer. So let me generate pool. One second. I guess pool is not working. Actually I guess you can type in your answers Here in poll it is not ABCD, na? So better you type in your answers. I am giving you 40 seconds, it is enough. Right? Hello?
Yes, sir.
Please type in your answers in the chat box. I am giving you 40 seconds.
So kindly show the questions.
Yes. So done.
Yes.
Yes, so many correct answers are there. Some wrong answers are also there. So basically what you are going to do is you are going to calculate the Coriolis component, which is nothing but 2 omega v. Right, here v is given directly. v1 with respect to 2 is 12 meter per second. Right, now omega, how you are going to calculate? From the rpm 2 pi n by 60. So from this you will have certain rpm like 4 pi or something like that. I guess rpm will be coming, right? Now when you go for this equation, finally Coriolis component, then it will be 2 into omega is 4 pi into this 12. So it is 96 pi, I guess. So 96 pi will come around 302, as many of you has answered correctly. Right? Correct?
Sir, direction of Coriolis component will be along the tangential direction only.
Yes. Hello.
Okay, sir.
Okay, now let us go to the next question. This one. Can you see this question on screen?
Yes, sir.
So I am generating poll for this one. 1 second. It is from 2013. 1 second. Option E, B, C, D. Can you see the poll? Can you see poll?
Yes, sir.
Yes, sir.
Now you can attempt this question. I am giving you 1 minute. You can calculate.
So can you show the question?
So done.
Yes.
So I'm ending the poll. Okay. So many of you get correct answer, right? Because here what we are going to do is absolute acceleration of the block at location A, right? So absolute acceleration चाहिए अगर, right? Then what we have to do is we have to have vector sum of this 2 omega v and omega square r, right? So 2 omega v will be in the direction perpendicular to this and omega square r will be along the link length. So once you calculate these values, you have to take sum of this both 2 omega v square plus omega square r, whatever vector you got, square. So 2 omega v will give you what? 2 omega v will give you 3, right? Because 2 into omega is 2 and this uniform velocity 0.75, right? So 2 omega v is going to give you this 3 and omega square r is going to give you this 2 square into 1 is 4, right? And this again this whole square under root of this will be your answer. So here it is 3 square plus 4 square, right? So that is nothing but 5, right? So this is the correct answer. Okay, so shall we move to the next question?
Yes, sir.
So here now you can see this question on your screen. I am generating poll for this one also. One second. I am generating poll for this one. It is from 2014 only, right? This one. Now for this again we will have A, B, C, D. Can you see the poll?
Yes, sir.
Now you can try and answer this question.
Done, sir.
Done. So let me end the poll then. So now let us see, many of you have answered correctly. So have you calculated like this only? Here as it is given that it, 1 second, let me draw it correctly. So what is given is, here you are having a 20 degree. Yes.
Sir, in previous slide, sir, answer is coming 34, sir. The previous question, sir.
Answer was 5 for the previous question, na?
Sir, 34 is coming, sir.
Sorry?
Sir, 30, sir, answer 30, sir, 34. Sir, answer is coming 34, sir.
I have solved this one, na? This question you are talking about? This question?
Yes, sir.
Ah, so you can see, na?
Yes, sir.
Okay.
Sir, how can, sir, 3 square, sir?
As it is given, na, values 2 omega v is 2 is there, then omega is given as 2 and this velocity is given as 0.75. So 4 into 0.75 is 3.
Yes, sir.
Okay.
Yes, sir. Yes, sir. Yes, sir.
Okay, so let us move to this one now. So here you are having this velocity of c is in this. Please mute yourself. Please mute yourself. Someone is there. Please mute yourself. Who is there? Please mute yourself. Suvendu.
Yes, sir.
Suvendu, please mute yourself. Hello. So let us. Please mute everyone. So here VP is in this direction as mentioned here. Now VQ is given at 45 degree. Right. You are asked to calculate this VP. VQ is given, right? Now this link is having this both the points P and Q. So as what we have discussed, if you take perpendicular to this and perpendicular to this, then this link is assumed to be rotating around the same point, this instantaneous center. Right, this you can write as IPQ, right? Now once you have this instantaneous center with you, you have this VP divided by this P into IPQ, that is the distance, right? Similarly VQ divided by Q IPQ. So you have to calculate this distance from this geometry, right? So here this is 20 degrees, so this is 70 degree. This link length is given as 2, so this will be 2 sine 70. Here this is perpendicular, so this is again 45. So as this is 2, this is 70, this is 2 sine 70, this is 2 cos 70, and here it will be cos, this particular can be calculated from cos 45 is equal to this x upon 2 sine 70, right? So when you apply this 2 sine 70 upon x, so if you further simplify, you will find this as root 2 into 2 sine 70, right? Root 2 into 2 sine 70 will be this from this triangle, right? This one. In this triangle, if you apply cos 45 is equal to this 2 sine 70 divided by x, then x will be your root 2 into 2 sine 70. Now this side will be root 2 into 2 sine 70 into sine 45. Sine 45 is again 1 by root 2. So this will be again, I guess, 2 sine 70. Right. So this way you are having all the datas with you. Now you are having this distance PIPQ with you and QIPQ with you. So if you put all the values, VQ is given as 1, So if you put all the data, your answer Vp will be coming as 0.96. So this is the correct answer. Right, so let us move to the next one. This one. Right. So here, can you type in the answers now? Here a rigid link PQ of length 2 meter rotates about the pinned end Q with a constant angular acceleration of 12 when the angular velocity of the link is 4 radian per second. Magnitude of the resultant acceleration means your two different component is there, right? R alpha is the tangential component and you are having the radial component as omega square r. You are having all the values with you, omega, alpha and r, and you can calculate the AR and AT, and then resultant acceleration will be AT square plus AR square. Can you quickly calculate and type in? Hello? Can you hear me?
Yeah, sir.
So please type in your answers.
Okay. Okay, sir.
Okay. So many of you are writing. Sorry. Here you are having AT equals to R alpha means what? R is given as 2 and alpha is given as 12. So you will have 24. Then omega square, omega is given as 4, so 16 into 2 will be 32. So when you square and add this 2 up, you will find 40. So many of you have written it correctly. So now let us go to the next one. Yes, this one. This one is simple. Right, in figure link 2 rotates with constant angular velocity omega, slider link 3 moves outwards with a constant relative velocity vpq, right, where q is a point on slider and p is a point on link. The magnitude and direction of Coriolis component of acceleration is given by can anyone answer this question? It is easy only, right? Yes, can anyone answer?
C.
No. Can anyone else want to try?
A, sir. Option A.
A is the correct answer. 2 omega v is the magnitude and direction of VQP is rotated by 90 degree in the direction of omega 2 only, right? This particular VQP is directed in the direction of this omega 2 in order to get the direction of Coriolis component, right? So 2 omega v will be in this direction. V will be rotated in the direction of omega, right?
Sir.
Yes.
Downward.
Sorry.
Direction of omega 2 is inward in the plane.
Direction of omega 2 is in the clockwise direction.
The vector in the plane.
Sorry.
The vector will be in the plane.
Plane only. These are all planar mechanisms only.
Sir, the vector of omega 2 will be into the plane, sir.
No. Omega 2 is having the what we can say clockwise direction.
So its vector will be into the plane. So rotating VQP in the direction of omega 2, that is into the plane. So it will be in the opposite direction, no, sir?
No. See, your VQP is like this. Your direction of omega 2 is this, clockwise. So you have to rotate this vector of VQP 90 degree in the direction of this omega. So this is how you will get your 2 omega v.
सर अगर कोई गलती से ये समझ ले कि ओमेगा 2 इनटू द प्लेन है तो सर मेरा तो सी आ रहा था तो वो गलत हो जाएगा ना.
Into the plane, I guess I am not getting why, because sir, all are planar mechanism. How omega 2 can be into the plane?
Sir, considering omega is a vector, so omega can be into the plane.
Which plane? Right now, whatever screen is there, you are telling is
into the screen, sir.
Okay. Then
Coriolis is
then
2 omega cross v.
see, then also if you take in that direction, then also how can it be opposite to the direction of omega 2? That I didn't get still in your case also. Whatever you are telling inside the plane,
हाँ सर, हाँ
inside
सर.
the plane, then also how it is opposite to this direction of omega 2? That can you
सर
explain?
क्योंकि ओमेगा क्रॉस वी होता है ओमेगा से वीपी की डायरेक्शन में, पर यहाँ पे क्या कहा गया है, वी क्यूपी को ओमेगा की डायरेक्शन में घुमाना है, इसलिए वो तो अपोजिट हो जाएगा ना.
No, 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 no. I don't know why you are getting confused, but here this one is the correct one, right? Answer A is the correct answer, right? So you can check, and I will also check.
Can you explain
whatever-
again, sir?
See,
Okay,
your direction of this linear velocity of q with respect to is in the outward direction. So in order to get the direction of Coriolis component, what you have to do is you have to give 90-degree rotation to your velocity in the direction of this angular velocity. It is clockwise, so this way you will have. Are you getting what I am saying?
Sir, yes, sir.
Huh?
Yes, sir.
Okay, so now let us go to the next one. Here also you have to type in your answers. What you have to do is, here you are having the road AB of length 1 meter shown in the figure is connected to two sliders at each end through pins. The sliders can slide along QP and QR if the velocity VA of the slider at A is 2 meter per second. The velocity of the midpoint of the road at this instant is, right? So that you have to now calculate. You have to assume one point at the midpoint of AR, right? And what you have to do is you have to calculate the velocity of that particular point. You have to calculate the velocity of that midpoint. Okay. Hello.
Yes, sir.
So please go ahead and calculate. You have to have instantaneous center method. You can use that.
Sir, R is moving.
Sorry.
Sir, is link R moving?
This both slider is moving, right? Both sliders are moving only.
The direction vector is not mentioned.
Direction, I guess here for A it is mentioned. For A it is like this only, right? For A it is already
Sir,
mentioned.
Sir, it's going to be 2 meter per second.
Let some others also calculate.
Sir, one thing, how the direction of B would be the on the right side direction, because if P rotates, then suppose R would be
Yeah, it
on
may be
the
inward.
left
It
side.
may be inward. It may be, yeah. Like, correct. But in short, it is in the horizontal direction. So in order to build your instantaneous center diagram, it is enough that whether it is inward or outward, but it is in the horizontal direction. So how you are going to start is, first you are having this particular points A and R, right? And from that, here as it is given in this direction, your this 90 degree to this will be like this, and here your 90 degree to this will be like this. So this way you will have your instantaneous center of rotation I13, right? Because here you are having your I23, here you are having your I34, right? Because see, this is considered as link 3, this road is considered, this slider is considered as 2, this slider is considered as 4, and this fixed link is considered as 1. right? So this is your velocity of A, this can be considered as velocity of R. So perpendicular to both this, when you take, then you will have this instantaneous center of rotation.
So which one is considered as one?
One is fixed link,
Q.
not Q actually. The sliders are sliding in this particular slots, na? Right? Here as you can
Okay,
see.
sir.
So that is fixed, is this fixed link, right? So
Then,
yeah,
sorry for interrupting. Then the B is also fixed, na sir?
B is not fixed, na? That slider is moving. A and B both.
Slider is moving. Then A and B, as you told that.
Yes. That is fixed. Yes. Correct. Here
Yes,
also,
sir.
here also it is.
A and yes, sir.
Yes.
That's
Correct.
what I meant.
Correct. Right. Now what you have to do is you have to calculate velocity of the midpoint, right? Here, this midpoint, that you have to calculate. So here you can call this point as C, right? So if you are going to calculate this velocity of C, right, then you can calculate it by having this angular velocity theorem, which says that VA upon I13A is equal to VC upon I13C, because this is a link, same link rotating about the point I23, right, instantaneous center of rotation. So this ACR is the same link. So velocity of A is this linear velocity, right? So I13A is the distance, right? And here also I13C is also distance. So omega is same for both this point A and C, right? Because it is rotating around the same point I13. That is why omega A and omega C can be written as VA upon this I13A and VC upon I13C. Now how will you calculate this? From the geometry you have to check. Here it is 30 degree, I guess, because this is 60. So this is 30 degree. Here this angle is again 30 degree, right? And this angle will become then 120 degree, right? This will become 120 degree. Now if you see the sine law in this whole triangle AR I13, right? If you take triangle AR I13, then 1 upon sine 120. Now this 1 is given, right? Link length AB is given. AB is 1 meter, right? 1 meter. So this 1 upon sine 120, this length and opposite angle. Similarly I13A upon this sine 30. So this will give you the dimension of I13A, right? This will give you the dimension of I13A. Once you have dimension of I13A, then you can check the triangle I13AC, right? So if you check this I13AC, then in that if you apply sine law, then here I13AC, this angle is 90 degree, this angle will be 60 degree. So in that I13C upon sine 30, I13C upon sine 30 will be equal to I13A upon sine 90, right? I13A upon sine 90. So as you have calculated I13A, you can calculate now I13C. So once you have I13A and I13C, and you also know that this VA is given as 2 meter per second, right? So VA is given as 2 meter per second, and you have calculated I13A and I13C, so you can calculate VC. So can anyone quickly calculate and tell me what is VC now from this data? Hello?
1 meter per second, sir.
1 meter per second. So all of you are getting the same?
Sir, one thing I would like to ask you that why the midpoint of the triangle is considered as a link number 3?
It is not considered as link number 3.
So you pointed it out as number 3, sir.
Actually, this is the whole link. AB is link 3. This slider is link 4. This slider is link 2. This whole link AB is this link 3.
Okay, now I
This
got it.
point is C only. This you can see.
Okay, got it.
Okay.
Sir, I have a suggestion. Sir, instead of going for two sine laws, will we be able to go by trigonometry that by symmetry, the triangle 30 degree, 60 degree, that is I13C, that triangle we can consider. And since the total length of the link 3 is 1 meter, and so half of it will be 0.5. So with that, we'll be able to calculate I13C and Y13A, sir.
I guess there are several ways of getting the different dimension from geometry. So whatever way you find easy, you can take that way, right? Okay. Now let us go to the next question.
Sir, I have a question, sir.
Yes.
Sir, after calculating the I13, how we are getting the VC, sir?
Sorry?
Sir, after calculating the instant center, how we are getting the VC?
From this angular velocity theorem, you are having this VA upon I13A is equal to VC upon I13C.
Yes, sir. Okay, sir. I understand.
Okay. Now, here, this is very simple question, right? Linear velocity of Q with respect to A, then it can be only one perpendicular component only, right? In case of velocity, you cannot have both the components along and perpendicular until and unless you are having a slotted lever and inside that your slider is there. So this option is correct, right? I guess this is easy.
Yes, sir.
Okay. So
Yes.
now let us go to the next one very quickly. Yes, this one. For this, you need to type in your answer. What you are asked is, for an inline slider crank mechanism, the lengths of the crank and connecting rods are 3 meter and 4 meter respectively. At the instant when the connecting rod is perpendicular to the crank, if the velocity of the slider is 1 meter per second, the magnitude of angular velocity of the crank is. So what you are asked is angular velocity of the crank, right? So this you can try, I guess. Right, this is.
So can you kindly go to the previous slide for a minute?
Sorry?
So can you kindly go to the previous slide for a minute?
This one.
Yes. Thank you, sir.
Okay. Now you can see this one. So first you have to have idea that what they are asking is, if they are asking in a slider crank mechanism, you are having your this connecting rod is at the 90 degree. Connecting rod is at the 90 degree, right, to the crank. This is the condition given. Now you are asked to calculate the omega 2, right, whatever it is, how you are going to calculate. You are given the slider's linear velocity, right? What is given? The connecting rod and crank's length are given as 3 and 4, right? This theta you have to calculate. You can locate instantaneous center, right, like this, right, I24. Here this is I23, it will be I12. Fixed link is 1 and this link is 2. I am rounding the link number because dimensions are 3 and 4, right? So this is link number 3 and this slider is link number 4, right? So 3 4 will be here instantaneous center, 1 4 will go to infinity, as you know. Now here this I24, why I have drawn this, because in case of this I24 I12 right into omega 2 is 1, because you know sliders linear velocity we have calculated with this only, right? At that time we were given omega 2, right, and we have calculated this. Now you are given this and you need to calculate omega 2 is nothing but the angular velocity of crank. Now here you have to calculate this I12 I24, this distance, right? So this distance you have to calculate from geometry, I guess. So for that what you can do is, first you can calculate this theta, that is tan inverse 4 by 3, right? Theta, tan theta is 4 by 3, so theta is tan inverse 4 by 3. So
27 degree, 53 degree.
53, right? Approximate, right? Then alpha you can have 90 minus theta, right?
37 degree.
This alpha will be 90 minus theta, approximately 37 degree. Now once you have this, then your cos alpha is equal to what? Cos alpha is equal to 3 divided by, because here also 90 degree angle.
Sir, 4 by 5 cos alpha 4 by 5 होगा.
Alpha is here na, in this triangle is having alpha. This
Sir, cos 30, sir, cos 37 degree तो 4 by 5 होता है ना?
This
sir,
angle,
cos 37
degree.
one
second, let me show you what you are calculating. You are calculating this distance na, you are having this distance as 3, so cos
yes,
alpha is equal to 3 upon this distance, I12
okay sir, जी sir.
I24,
yes, sir.
Correct? Are you getting now?
Yes sir, yes sir.
So from this cos alpha is equal to 3 upon I12 I24, you will find the distance I12 I24. So what is this distance? Whatever you are getting from this 3 upon cos
15 by 4,
whatever is this, you can calculate this, and once you calculate this, then you can calculate omega 2, because omega 2 will be 1 upon this distance I12 I24.
Sir, I am getting value of omega 0.267, is it correct?
Yes, 0.266 is the answer. So 0.266 or 267, whatever is the correct answer, right?
Yes sir.
So are you guys done? Hello?
Yes sir, yes,
Yes, sir.
So you got this one, right?
Yes, sir.
So now let us go to the next one. So
Sir,
yes, yes.
please move into the previous slide, please. For
1 second. This one.
okay. Yes, sir. Yes, sir.
Okay.
For a moment.
Hmm.
Okay. Now done.
Okay, so now let us go for the next question. Again you have to type in your answer. Let me read the question. Block 2 slides outward or link 1 at a uniform velocity of 6 meter per second as shown in the figure. Now link 1 is rotating at a constant angular velocity 20 radian per second counterclockwise. The magnitude of the total acceleration of point P of the block with respect to fixed point O is. Total acceleration you have to calculate. It means you have to calculate again those two components, centripetal, Coriolis component and that this centripetal component, right? So once you calculate these two components, then you can square them and add and under root them. That will be your answer. You have calculated this kind of question earlier also, right? That 2 omega v is one vectorial component and r omega square is the other vectorial component. So omega is given as 20 radian per second. This velocity is given as this 6 meter per second, right? Omega is given as 20 radian per second. So 2 omega v can be calculated, and then from r omega square you will be able to calculate this component, because r is mentioned over here 100 mm, that is 0.1 meter. Omega is anyway given 20 radian per second. So are you guys getting what you have to do?
Yes, sir.
So please calculate.
So it's coming 243.
243.310, yes, because
Yes.
your 2 omega v will come around 240 and r omega square will come around 40. So when you square and add them up, right, 240
40 to 37.
plus 40 square, like 243.310 or something like that is coming, correct?
Yes, sir.
Okay, so now let us go to this last question. Yes, here in a slider crank mechanism, the length of the crank and the connecting rod are 100 mm and 160 mm respectively. The crank is rotating with an angular velocity of 10 radian per second counterclockwise. The magnitude of linear velocity of the piston at the instant corresponding to the configuration given in the figure is, you have to calculate magnitude of linear velocity of piston, right? So Vc you have to calculate, that you know that is omega of this crank, right, and instantaneous center, whatever I12 I24 is, right, that will be your answer. Here if you draw the instantaneous center, that your I24 will lie on the same point as I12, right? So sorry, I12 is here, I24 will lie on that point only, I12 will be here only, because this is link 1, right, this is link 2, this is link 3 and this is link 4. So I12 will be here only, but I24 will lie here, instead of extending it and all as you were doing it previously, right, in previous slides. If you see, you are doing it by extension, right, this I24. Are you getting what I'm trying to say?
Yes, sir.
So I24 will lie on this same point here as point B, right? So now it is easy, right? Omega of crank is given, I12 I24 distance is given, so directly you can calculate Vc. What is your answer?
1 meter per second.
Sir, this is 1.25 meter.
1 meter per second, na? Because crank is 10 radian per second, omega crank is 10 radian per second, and this distance is 100 mm means 0.1 meter, so 10 into 0.1 will give you 1 meter per second.